Colleagues, friends, good afternoon. Welcome to this very luxury conference room. And today we have great pleasure to have Professor Zhao to come to visit us and to give us a talk. And I'm given a very long list about Professor Zhao's achievement, but I will make it short. The main reason for inviting Professor Zhao as the VIP for peer, because he's the senior fellow of peer academic, right? And also he's the chair of our international advising committee for RISE, that is a smart research institute for smart energy. So this is the most important reason. Besides, it got a long list of reasons. Professor Zhao is the chair professor of mechanical and engineering in the South University of Science and Technology, that is SUSTech in Shenzhen. But before he joined SUSTech, he was quite a long time as a chair professor in the Hong Kong, Hong Kong University of Science and Technology. And very importantly, he is the academician of the Chinese Academy of Science. And of course, as I mentioned, the senior fellow of peer. So it's equally important as the fellow of the Chinese Academy of Science. And he have many academic and societal impact and achievement. I will not introduce one by one because I think the report of Professor Zhao will give us the details. But besides, he's the fellow of the American Society of Mechanical Engineering and the Royal Society of Chemistry and the Chinese Society of Chemistry. And he's also the editor-in-chief for International Journal for Heat and Mass Transfer. So you will find Professor Zhao have a great achievement in the multidisciplinary energy research and application. So I will not give the details, and I give the floor to Professor Zhao. Let's welcome Professor Zhao for his.
All right, colleagues, friends, fellow students, we really pleased to be here today. And thank you very much, Professor Wang, for your very generous introduction. And very good to see you, Professor Mai, and other friends here today. So I'm talking about energy storage. So the key words, my title here is fuel cells and long duration energy storage. So over three key messages here today. First of all, I'm talking about energy storage for achieving carbon neutrality is very demanding. Okay, so this is the first point. And another point is the further increase in the penetration of solar wind is calling for new concepts and the strategies of storage, especially for long duration storage. And finally, I talk about fuel cells. Okay, fuel cells is something very important. Solar and wind using fuel cells is very promising. So this is the 3 points I'm going to share today. First of all, let me start with a broader perspective. Talking about goal of carbon neutrality. We all know that China, the mainland, has proposed to achieve carbon neutrality by the end of by the year of 2060. So this is something very revolutionary change because the energy is going, energy structure is going to be changed. So basically, we to move on, we need to transition away from fossil fuels and significantly increase zero carbon renewables such as solar and wind. So right now, in the mainland, solar wind just counts for 5% in the current energy mix. So to achieve the carbon, so-called carbon neutrality, or is called net zero target, the solar and wind need to be increased to 60%. So then it will be relatively easier for us to achieve the target of net zero. So this is going to be a big change. It's a big shift in our energy landscape. And so where we are today, so it's very impressive that over the last 20 years, solar PV developed so rapidly. And the efficiency of solar PV can now be as high as 30%. Particularly the cost is very cheap now. It's cheaper than fire-powered power. So particularly the installed capacity of solar and wind in the mainland has already exceeded to over fired power. So this is very, very exciting. So the cost is cheap, is much lower, and also capacity is very, very high in a whole country. But the bad news is that there exists big gap between installed capacity and on-grid power. So the on-grid power means power generated by solar PV and wind turbines only count for 20%, although the capacity, installed capacity is 40%. So this big gap. So this is a problem in our use of renewable energy such as solar and wind. So what causes the gap? It's not the problem of solar PV. It's not the problem of wind turbine. Is the challenge lies in intermittent nature of solar and wind resources. So this is the problem: intermittency, unstable. So therefore, the power generated by solar PV and wind turbine cannot be completely integrated to the grid, and a large fraction of that has to be curtailed. So that there is a term is called wind and solar curtailment. 气风气光 is very, very popular terms in the industry, ranging from 5% to 30%. So this is really a big economic loss. So the question now is how to tackle the intermittency of solar and wind. So this is a challenge issue. So because of that, and people turn to the energy storage solution, because energy storage can accumulate and stabilize, intermittent power, and finally you get power as needed. So basically, we get a storage facility which can convert fluctuating uncontrollable electricity and heat to stable, controllable electricity, heat, or fuel. So different forms for energy storage. So so this is going to mean energy storage can facilitate the balance between electric supply and demand. So energy storage can enable 100% renewable electric grid, and hopefully can kill in the future kill the fossil fuels. So storage cannot be missing in the future power utilities. Okay, this is a big change in the future. So currently, for example, the lighting here, the electricity power the lighting here was just generated just a moment ago, because the thing is the way things stand out today is demand. Electricity demand must be constant balance with supply. But in the future, the power may not come from generators, from solar PV wind turbine directly, but from storage facilities. So this storage is so important, and storage will be used in every step in the new power systems. So in a generation and storage will be help to integrate renewables such as the wind and the solar and the supply peaking load, avoid power disruption, and also solar and storage can be used in a grid and also other use, okay, very different functions. So demand for energy storage towards carbon neutrality is huge. Okay, it's going to be a $1 trillion industry. Okay? It's very, very exciting industry. So, but the energy storage devices I'm talking here today is not the battery for power your smartphones or electric vehicles. It's something very big. We are talking about megawatts, even gigawatts hour storage station. So therefore, for this very big energy storage devices facility, we need to make sure, first of all, it must be safe and reliable. Okay. Fire mobile phone or EV is a thing, but you will never don't want to see megawatts energy storage get fire. So it's going to be disaster. So safe is very, very important, safety. So secondly, energy storage devices technology must be cost effective. So a lot of things affect the cost, like capital cost, and also in the run storage devices efficiently, and also long cycle life. All this affect the cost. So another thing is that technology, a facility needed to be flexible in selecting sites, okay? Because we get solar everywhere. So, and also resources must be, not too many limitations for particularly for the material used for the energy storage devices. So therefore, the 3 key requirements for grid scale energy storage. In addition to that, we all know that the sun is not always shining, the wind is not always blowing. So renewables intermittent period can be last for dozens of hours. Okay, so this, for example, the wind power can experience intermittent period lasting to up to 50 to even 100 hours. Okay, similarly for the solar resources also has the encounter intended period of low sunlight levels lasting for even several days, even weeks. So this means that in the future, when solar and wind become predominant energy sources, we need to have long energy storage. Because this is the reason I'm talking about long energy storage here today. So this is a new watchword, and because long duration storage can prevent curtailment of renewables, such as wind and solar, particularly can offer greater flexibility and resiliency. So what is storage duration? Basically, it's a time period over which a storage facility can discharge at the condition of rated power. Okay, so when a facility and when technology can discharge above 8 hours, we call that as long duration storage. So the question now is, how can a storage facility be long in duration? So let me compare 3 storage technology right now in use. Okay, that's including pump hydro, compressed air, and lithium-ion battery. Three technology here. So whenever we talk about storage technology, the first thing we need to know is what is the energy carrier used for that particular technology. So for pump hydro, the energy carrier is water. So we use water as energy storage carrier. So what is a fluid which is flowable? Okay. So because of this flowable energy carrier, we can get energy unit and power unit be decoupled. So this is because we get water as a flowable energy carrier. So therefore, because decoupled energy and power, pump hydro is very flexible in storage duration. So basically, the storage duration depends on how large your reservoir, your back. So this is the advantage of pump hydro. So pump hydro is also relatively efficient, around 70%, 75%, and also is very long cycle life. Okay, but the thing with pumped hydro is set limitation. Not everywhere you get water, you get kind of mountain or something, okay, which is a very limited resources. So, and sometimes pump hydro can also be impacted by climate. So this some things we need to consider for pump hydro. So another technology is compressed air. So for compressed air, for the first thing, the more important thing is that compressed air also use flowable energy carrier, that is air. So air is fluid, is a gas, can be fluid. So therefore, similar to pump hydro, compressed air also has an advantage, flexible in duration. So duration for compressed air really depends on how large your storage of air. So this is the advantage of compressed air. Compared to pumped hydro is less efficient, so usually about 50 to 60%, but it's very long cycle life, and it's set limited because it's hard to find the place to store the air because we need a very big space for store the high pressure air. Now let's look at lithium-ion batteries. Lithium-ion battery is very high tech, is very efficient, very energy dense. It's the big advantage. But the energy carrier for lithium-ion battery is not a flowable energy carrier. Okay, the space is is kind of solid, cannot be fluid. So therefore, in lithium-ion batteries, the energy unit and power is closely coupled, cannot be decoupled. So that therefore, lithium-ion battery is not that flexible in storage duration. And but lithium-ion battery is kind of electrochemical energy conversion device. It's the benefit is very efficient, very energy dense. So that's a very important thing. So when you compare these three technologies, you get some insights. First of all, if you want to get long duration, you want a flexible duration, then you need to get flowable energy carrier, for example, water and air. And if you want it to be efficient, set flexible, you need electrochemical kind of energy conversion devices, such as lithium batteries and other electrochemical devices. So when you integrate these two things together, then you will be able to create kind of efficient, long duration, set flexible storage technology. So what is that? It's fuel cells. So the keyword my talk today is fuel cells. What are the fuel cells? Fuel cells just electrolyzers, okay? Electrolyzers are used for generate electricity, generate hydrogen, okay? Fuel cells, okay, is another type of fuel cells. fuel cells for power generation using hydrogen, methanol, ethanol, and also fuel batteries. Okay. So why we get a general term fuel cells? Because all these devices, you get electrolyzer, fuel cells, fuel battery, they share the similar working principle, similar structure, and similar research issues. So over the last 20 years, I have been working on all these fuel cells. So the flowable ion carrier for the fuel cells have, for example, existing technology. You got hydrogen, you got methanol, you got ammonia, you got a liquid electrolytes. All this, is flowable energy carrier. So fuel cells, because you have flowable energy carrier, it allows you decoupling power and energy. So therefore, you get a flexible duration. Fuel cells are very easy to scale up. Fuel cells, because it's electrochemical device, is very efficient, and also no site limitations. So therefore, fuel cells are promising for storing solar and wind. So let me talk about first example of fuel cells. That is a hydrogen storage technology. So hydrogen storage technology is to store energy using hydrogen. So the energy carrier here is hydrogen. So basically, we use electrolyzer to convert electricity to hydrogen, and hydrogen feed to fuel cells for power generation. So the whole process, whole cycle is no carbon emission, and is very efficient, a high energy density, long duration, because it's a fuel. Hydrogen is a fuel. You can store hydrogen as long as you much. Okay. No site limitation. Electrolyzer and fuel cells can be installed anywhere. But the challenge for hydrogen storage right now is the cost. Cost comes from storing hydrogen and transportation of hydrogen. Hydrogen is the lightest element in the natural world. So it's very, very challenging to store hydrogen, to transport hydrogen. So right now, fuel cells, over the years is, rapid development, is relatively matured. The cost also can be very low. But right now, the bottleneck of this technology, hydrogen storage, is transportation of and storage hydrogen. This is the problem. So another example, which I'm going to emphasize, is another example fuel cell is redox flow batteries. So this, I'm going to talk more about this today. So redox flow battery is different from our conventional lithium-ion batteries. So the energy in flow batteries installed in liquid electrolytes. Liquid electrolytes, it's a solution. It cannot be burned. Okay, it's completely safe. No any safety problems. And as you can from this sketch, that we have two tanks, one store for positive electrolytes and other for negative electrolytes. So so that energy is decoupled from batteries, from the power units, so that it's very flexible in duration. So the duration really depends on the size of your tank. And also it's a battery, so it's set independent. You can store battery anywhere. It's very durable. Its second life, it can be 20 to 30 years long. Okay, so therefore it's very exciting technology suited for large scale energy storage application. But right now the issue with flow battery is the cost issue. Okay. So we needed to reduce the cost. So over the years, we have been working on to reduce the cost of flow batteries. So our idea is to increase the current density. So increase in the current density means the increase in power density. So when you get a larger power density, means that the required amount of materials for construction stack will be smaller, and so that the cost will be reduced. In the meantime, when you get a higher current density, means that you get a higher electrolytes utilization, because the material for the electrolytes, some materials is expensive. So therefore, currently it's only 60% of the material be used. Okay, so we need to increase this utilization of electrolytes so that the cost can be reduced. But it's challenging to increase the performance of fuel cells, such as flow batteries. Okay, so because for fuel cells, basically it's not only material problem, it's not only electrochemical, electric chemistry problem. It's kind of we need the knowledge of heat and mass transfer. So that's why 20 years ago I moved to work on hydrogen fuel cells, methanol fuel cells, and over the last 10 years I have been working on flow batteries and other things, because this device needed a interdisciplinary knowledge crossing materials, electrochemistry, and thermofluid science. Okay, so material side, for any fuel cells, hydrogen fuel cells, or flow battery, we have needed material for electron conductor, active materials, and also ion conductors. Okay, so this is the material problem. But when you get the material ready, you need to form the microscopic structure to get so-called triple phase boundaries to increase the electrochemical reaction rates. In the meantime, you get a porous structure, porous electrodes, and so that this is going to transport, electrolytes for flow batteries, hydrogen fuel cells. And in the meantime, you need to maintain temperature at optimal temperature level, so that you need the knowledge heat transfer. So this is, it's a mix of many different, backgrounds, but subjects, so that we need to tackle these challenges. So, so over the years, we have, worked on fuel cells, flow batteries from fundamental to system developments using so-called interdisciplinary approach, materials, electrochemistry, and thermofluid science. So we started a mechanism between the interplay between heat and mass transfer with electrochemical kinetics, and from theoretical framework, and then we rationally design and develop key components, and also cells, and also systems. And so that with that we will be able to reduce, increase the performance and reduce the cost. So over the last 20 years, my research basically is to integrate electrochemistry with thermofluid science, and we get a thermoelectrical theoretical framework, which allows us to make breakthroughs in fuel cells, flow batteries, and other metal ion batteries. So with the theory framework as a guidance, we have many breakthroughs in flow batteries. Okay, for example, membrane. Membrane is the key component of flow battery, which separates positive from negative side. So that for the flow batteries, it's different from fuel cells. For fuel cell, hydrogen fuel cells, we get one ions, just proton. But for flow batteries, we get multiple ions. It's multiple ion technology, okay, devices. So we need a very high the conductivities. In the meantime, we need to have a selectivity of ions, okay? And because it's different ions in a system, okay? We just want the desired ion to pass through the membrane. So this is a challenge. This is a contradictory thing. We need to maintain higher conductivity. In the meantime, higher selectivity. So our technology can make it and can get a perfect membrane. So another thing is that electrodes. Electrodes is another key component for flow batteries. So for electrode design, we need to get a surface. Surface need to be very active to enable a faster electrochemical reaction. But in the meantime, has to be inert for side reaction. So sometimes we get hydrogen involution in the charging process. And for the design of electrodes, another big thing is structure. Okay? So we need to have higher specific area and for speed up the electrochemical reaction. But in the meantime, when you get a larger specific area, means that the void, the poles are smaller. So this is going to increase the flow resistance. So therefore, we invent a so-called multi-scale electrode, and which allows very high specific area, but in the meantime, we get a very low flow resistance. Okay, so this allows the tremendous increase in energy efficiency and also power density of electrochemical, current densities. So our cells can run very long period. It's over 50,000 cycles. So it's actually is a world record. Okay. And also in performance, right, the power density of our flow batteries can be as high as 2.75 watts per cm square. So this is really very high power densities. And this is what we got this flow battery stack. So the feature of this flow battery energy storage technology is very safe, high performing, and long cycling life. So this just the technology what we are developing flow battery. By the way, the flu is created by myself. I learned that flu last year. All right, so I just talk about the flow batteries. Now I got another thing to talk about. So just now I mentioned many times about the energy carrier. Okay, so energy carrier is so important for energy storage. Actually, oil is an excellent energy carrier. Oil is outcome of stored solar. Okay, it's energy carrier for solar. But oil is a liquid, so it's very, very easy to be used. But formation of oil is very sluggish, okay, meaning it's yields. So we are talking about the energy, renewable energy, not renewable fossil fuels. We talk about the time size, okay, time scales. So if it's too long, then it's not renewable. So oil is not renewable and also get carbon emission. So, but it's kind of a liquid energy carrier. It's very good to use. So, so that can we invent something even better? Okay, alternative, clean, renewable, efficient liquid energy carrier. So basically, we invent something exciting. So we invent a liquid energy carrier. Basically, this liquid energy carrier can be electrically charged and discharged. So it's called electrical rechargeable liquid fuel. I call that as e-fuel. Okay. So with this e-fuel, we have different material to form this e-fuels, inorganic e-fuels, organic e-fuels, and nanofluid e-fuels. So different e-fuels have different applications. So when you're ready, when you get a e-fuel ready, then you will be able to form a completely new storage system. So basically, it consists of e-fuel itself. Then you get an e-fuel charger and e-fuel cell. So e-fuel cell is to generate electricity using e-fuels. So e-fuel get its electricity from solar PV and wind turbines. So basically, we can use the power generated by solar PV and wind turbine to charge e-fuels. So the charged e-fuels can be stored as long as you wish, because it's just like a fuel. Okay. So e-fuel charger has no set limitation. So you can anywhere install the e-fuel charger for charging e-fuels. So the charged e-fuels can be readily, it's a liquid can be readily dispatched to anywhere you need. For example, so when you get e-fuels, then you e-fuel cell generate electricity because it's stable, so that it's relatively easy to integrate the grid. And also e-fuel cell can power off grid. Okay. Something more exciting is that e-fuels maybe in the future can propel vehicles. Okay, but right now the energy density of e-fuel cells is not that high enough, and so that. But my dream is to use e-fuels to propel vehicles, e-fuel cell vehicles in the future. So overall, from charging to discharging, it's just electrochemical reactions process. Is very efficient. Okay, so so basically with that idea, we have a developing e-fuels, e-fuel charger, and also e-fuel cells. So here is some results. As you can see, this very efficient e-fuel charger. So the charging efficiency of e-fuels can be as high as 92% to 80%. It's much more efficient in charging as compared with flow batteries. And e-fuel cells is very powerful because power density is very high and very high efficiencies to charge to generate power. It's 3.5 watts per cm squared. So we compare e-fuel cells with the conventional fuel cells. So conventional fuel cells, hydrogen fuel cells, methanol fuel cells, all need platinum as a catalyst. But e-fuel cells does not need any expensive metals as catalyst. But even that, the power density e-fuel is much higher than conventional proton exchange membrane fuel cells. So this demonstration of e-fuel systems, basically the up one is a stack for power generation. The lower stack is for e-fuel charger. So here are some advantages for e-fuel storage. First of all, it has no set and time limitations. So because e-fuel charger can charge e-fuels anywhere, anytime. So also, fuel cell is very efficient to generate electricity anywhere needed. Okay, so it's a no time, no set limitations. So it's very efficient. The round trip efficiency of fuel system can be as high as 85%, and very high power densities. And it's because we got two different charger and fuel cells. It's relatively easy to scale up and adaptable. So it's completely safe, environmentally friendly. So therefore, it's going to have its impact in the future. So we compared different technology in terms of duration and power. So here's the lithium-ion batteries, here's the flow batteries, and here's the pump hydros. And here is e-fuel storage. So it's much range of applications in terms of duration as well as power. All right, I think this is my last slides. I sketched these drawings 20 years ago, okay, when I started working on fuel cells, okay. And now I realize this very important sketch I drew 20 years ago, because it's basically the electrolytes for electrodes structure for fuel cells, for example, fuel cells, flow batteries, and other flow cells. So in this electrodes, you need to conduct electron, you need to conduct ions and mass, and also we need to conduct heat. Okay, so it's very challenging to design this the structure. You need to make sure that it's very efficient, very high power, electrochemical reaction rate. Then any of the flux, mass, electron, and ion can be limited step of electrochemical reaction rate. So that when you change the structure to speed up one flux, this is going to be affect other flux. So therefore, it's very challenging to get a perfect design of electrode structure for fuel cells. So we are still working on these directions and trying to get a revolutionary change by a perfect design of electrodes. And it's last month, no, it's in May of this year, I gave a very long lecture on CCTV and talk about ion storage industry. And as the end of my concluding my remarks, I use a very short slip. This okay.
过去10几年来，我们国家在光伏和风机技术方面取得了突破，装机容量迅速的提高。但是，目前我们面临的挑战是储能。我们能够在光伏和风机技术上取得突破，我相信同样我们也可以在储能技术和产业发展方面取得突破。给力的光伏加风机加储能，将使我们充满信心，迈向碳中和时代。谢谢大家。
Thank you, Professor Zhao, for very informative and very interesting lecture. So today we have, I think we have many questions, probably some of the challenging questions to you. Anyone like to start first? I think Professor Nimong, I'd like you to start first. Yeah, because you're working in the similar area.
Okay, thank you, Professor Zhao, for your very nice talk. I think I learned a lot from flow cells. I just want to know, in your future research, are you going to incorporate other techniques like AI in your design of flow cells? Yeah.
All right.
Can you share some information about that?
So nowadays AI is so powerful, so popular. Everybody talk about AIs. Actually, we use AI machine learning for the design of the components in flow batteries. That is a flow field. We use that machine learning trying to create a structure which can be, the target of the design is to make sure that it's minimum work at uniform distribution of electrons onto electrodes. So this is the target, and somehow we get a kind of solution. Okay, it's the students work on that the project for 3 years and get something very exciting, design, and but it's very time consuming because we just I'm not good at using AI machine learning, but the students just work on that. I just give the task, how to calculate the flow field to be uniform in distribution of electrolyzed onto the electrodes, and also how to minimize the flow, pump work. So this is a target. I think this is a trend. Okay, machine learning can help a lot of things in research. Yeah.
Yes, Professor Zhao.
Professor Zhang, thank you very much for your very inspiring talk. So I have 2 questions. The first question is a technical question. So I'm very interested in the flow battery stack you built, because I think it's significant for the large application, large scale application. So I'm just wondering how, sometimes because I'm at the energy use side, so sometimes we need to control the discharge rate from the battery. So in terms, if we build such a large scale battery storage system, so how we can control the discharge rate, so that to make sure it can follow the, for example, the building power demand change. So this is the first question. Maybe, yeah,
So you're talking about the application for storage in buildings.
in buildings or in other
In the power grid.
changing load,
the power grid.
the load, the demand, electricity demand is changing. So the discharge rate should also be controllable to follow the change of the
So, okay.
Uh.
So storage basically is to help you get get flexible, control the grid balance, as I mentioned, to balance the supply and the demand. So this is the reason we need a storage. Okay. So as I mentioned in my talk today, we have different technologies for different applications, scenarios. For example, we need storage in a generation side. We need storage in a grid side, and also end use. Okay, different site. It's going to be different technologies. For example, usually hydro pump can be used in a generation side and also grid side, but it cannot be directly used in the end use side, because it's too big. Compressor also have the similar things. So and use side, usually we use batteries, but the battery now is that over the last 2 years in the mainland, there is a tremendous increase in installation of energy storage devices, but particularly it's predominated by lithium-ion batteries because it's very cheap now. The cost of lithium-ion battery is cheap. But the one thing is that the utilization of installed storage is very low. The reason is because first is because the duration of lithium-ion battery is short. It's less than 4 hours. Because the increase in the fraction of solar wind, you need to increase the duration. And also because lithium-ion battery is not reliable, is not that completely safe. So the safety is a big problem with lithium-ion batteries, as well as the second life is another big thing. So, but when we talk about the flow batteries, it's completely safe. We actually demonstrate the flow battery in Shenzhen, in underground, a building underground, so can be used for and use applications. Yeah. So yeah.
Yeah, that's great. So I hope I can have the opportunity to visit the large scale storage site. Yeah. So my second question is a general question. So I know you are very successful in academic research. So I can see in your research you have interdisciplinary research, the thermophysics and the electrochemical. So from those, actually, we can see it's very fundamental research. So it's very easy to tell very good story when we prepare research proposal or we try to promote our research. But for me, actually, I work on a very applied energy field. So sometimes I feel it's very difficult to persuade people that my research is also significant and also can make some breakthrough. So I just want to hear your some advice, suggestions, how we can highlight the innovations in the applied research related to energy. Thank you.
Yeah, this is a tough question. So
he's asking the help for to help her to get some success in big funding.
Yeah, even research Professor is very successful, professor in the world class scientist. He will tell you the story about his successful stories. So basically, I think people are working on different fields, right? Different. Some people emphasize the fundamental side. Some people emphasize applied research. I think it's hard to compare. Both are very useful for very even for applied research. You get something very exciting. For example, you can construct something very exciting. The thing is that you need to get innovation. Professors, I think in the university, need to work something new. Even for applied, you need to work something new, and you get it. Try to strive yourself for new things, even the applied side. Yeah. My research actually 20 years ago, I didn't know that fuel cells, flow battery become so hot today. I did not realize. I just find it's interesting because I have been working on, heat mass transfer, for many years, and I get bored. it's not that exciting, but finally, one day we find out fuel cells is so interesting, and you get electricity from fuel. In the meantime, you get a heat transfer problem, you get a mass transfer problem, and it's just integrate all the things together, so that I just work on fuel cells as beginner, and it's just by chance. Finally, today I find out that it's so exciting, so important. Very beginning, I didn't realize that is going to become something today. But just driven by interest, if I find something interesting in a fuel cells. Yeah. So sorry, I cannot give you too useful ideas. Yeah. Professor May can provide something. Yeah, Professor May is very, very successful, world-class scientist.
We organize another session for you to share your experience.
Yeah.
the department.
Yeah. Yeah.
So we produce actually 3 academicians in my department, right?
Yeah. Yeah.
We can talk about that. Because he's the main speaker here.
Yeah.
You can become the fourth. So, more questions?
Thank you, Professor, for giving a very wonderful presentation about energy storage. We have been working in this area for several years. I just visited a wind farm, very large wind farm in Inner Mongolia, near Hohhot. The abundant rate of wind and solar is about 40%. Very, very serious. They simply shut down the turbines and the solar PV panels. My question is, I think the energy storage topic is very important for research and development, as Professor Zhao mentioned. My question is, what do you think about the cost? Which one? I think water, pumped energy storage may represent the future large applications. Which technology is cost effective? What do you think in the future?
Thank you very much, Professor Yang, for this good question. So cost is one of the things, one of the requirements for energy storage technology. But we needed to, sometimes we need to make a compromise, okay? So talking about the cost, right now, lithium battery is cheap. Okay? Lithium battery industry is matured, and because of the development, rapid development of EVs, batteries. And, but we now installed many lithium-ion battery and storage stations in the mainland. But just now I mentioned that the problem is that the safety problem, and people are afraid of, explosion or fire, and the utilization of this is very, very, is limited. Okay, so safety is important, cost is important, and also another thing is about the site and flexible. Okay, you need a selection of sites. Pump hydro is very reliable, pump hydro. Okay, but you need water, right? Particularly in the Mongolia, you're short of water, right? So site limitation is a natural resources limited the application of pipe hydro and compressed air. So in my view, if our technology, flow batteries, the cost, because we have been working on that, we now can make the cost very close to lithium-ion batteries. Okay, closeable. But it's not, you cannot just compare the capital cost. Capital cost is still higher than lithium batteries. But because flow batteries have very long cycle life, okay, 20 years cycle life, and so that the cost over the whole life will be smaller, okay, as compared to lithium batteries. But the most important thing is about the flow battery is very safe. It's no safety problem, and it's scalable. It can be used anywhere. Can be generation side, can be grid side, can also be end use side. So it's have many different application scenarios. So I think the future you will see that flow batteries will make its impact. Yeah.
Thank you. More questions? I particularly wish to have some. Oh yeah.
Thank you, Professor Zhao, and I'm a PhD student in thermal engineering. So I have actually I'm not in the let's say battery field, but I have one question. Like you mentioned the flow batteries, like redox flow batteries, their power there is dependent on the size. Basically, we can have a larger tank. Then we can store more like electricity, right? So I have something in mind, like can we like make a complex system, like we distribute the electrolytes to different sources. For example, we source electricity from solar and wind and other sources simultaneously, and we also build a large like a hydro system to distribute the electrolyte to the all kinds of buildings, and we use it simultaneously. Is that possible? I just have something in mind.
It's an excellent idea. But when you use, because electrolytes, it's kind of energy carrier. So basically you charge the electrolytes means that the energy goes into the electrolytes, okay? So as an energy carrier, one requirement for energy carrier is need to be energy dense. So means energy density need to be high enough. When you just transport water, very small amount of energy, then it's going to be less efficient. So if you get a very energy dense liquid electrolytes solution, this excellent idea. But currently the energy density is not that high. So when you transport that to different areas, it's going to be you need pump. Okay, transport need energy to pump that. Yeah.
So it means the pump power, like
yeah,
it's
cannot compensate all
okay. I understand.
overall efficiencies. Yeah. So it's a good idea. So in the future, if we get a very energy dense electrolytes, then your idea will be realized. Yeah. Workable.
Yes.
Okay, thank you, Professor Zhao. Thank you, Professor Wang, for this exciting event. Okay, for old friends gathering and all making new friends. In fact, I got 3 questions. The first one, in fact, we know the importance of energy storage. So I'm also working in this field, but it's phase change materials, it's thermal energy storage. So what's your comment on the contributions, or it can be an alternative? Okay, so regarding energy storage for solar and for wind, so for the curtailment, that's my first question.
So you're talking about the thermal storage.
Yeah.
Okay. You need me to compare or what?
Do you think, because you mentioned all our fuels, I think mainly and power.
Yeah.
So it's,
Okay.
do you think?
Yeah, right. So thermal storage is also very important. Because first of all, thermal storage can have a very long duration. But it really depends where you install, where you use this thermal storage. For example, in north part of China, mainland, in winter, wind resource is very high, very rich. Yeah. You get a very high speed of wind in winter. But you need to provide heating. Okay.
Okay.
So heating is a problem in winter. In the past, we just burn coal for providing heating, right? So now you can use the thermal storage. You can turn the wind power into a heat. And then this heat can be used to provide heating for buildings, for many different.
It's simple.
It's
simple.
Yeah, it's much simple because and use heat. Okay. But if you convert heat back to electricity,
it's difficult.
Then you need to think about it, the efficiency.
Okay.
So electricity to heat to electricity, then efficiency will be.
Depending on the demand side, if it's really heat.
If the other side is end use is heat, then heat storage, thermal storage will be will be very, very
Then
important.
I'm asking my second question
Sure.
is about, now Hong Kong government, our university encourage us to translate our research into, commercial market. So what's your successful experience to translate your fundamental research into large scale?
I'm not that
It's
successful.
totally different.
So I'm working right now. When I get to Shenzhen, the reason I moved to Shenzhen is to try to push my technology can be transferred to the market.
Okay, then it's me. If we want to translate our research, we need to go to mainland China.
You can here you can still work on that. That doesn't mean that you needed to move out from Hong Kong. It doesn't mean that. So you can still work on in Hong Kong for transfer your technology. It's no
Okay,
problem.
I look at Professor Ni and what's his supporting policy for us.
But it's relatively easy because industry in Shenzhen, in mainland is.
Okay, my third question is about for your video, the background music.
Yeah.
So it's very old, for me, very traditional, very old. You cannot attract young peoples here.
Oh, okay.
So that's you blow the flute, the music?
Because I am very traditional. I know that music. I've played this flute last year, just 1 year.
That's your own performance music.
Yeah. I
Okay,
started run the flute music last May. Yeah.
I think maybe you try to attract young people like Professor Wang.
Sure, I'm going to
Maybe
learn.
it's
I'm going to learn. Yeah.
percussion.
I'm going to learn. Yeah.
Okay, thank you.
Yeah, thank you.
Thank you.
Yeah.
Yeah.
Good suggestion
please.
for my flute playing.
Yeah, so thank Professor Zhao for the nice talk. I'm a visiting scholar working on fuel cells. So I have two technical questions. The first one is about the lifetime. So you mentioned that lifetime is about 20 to 30 years. So how do you predict or measure such a long lifetime in practice? Because when I read papers about fuel cells, very few people run the system for 20 years and say that our lifetime is 20 years. How do you do that?
Okay. So flow batteries, I'm talking about flow batteries. I didn't talk about the second life of fuel cells. So flow batteries, can be as long as 20 to 30 years. The reason is that because flow battery is just the electrolyte just flows through the electrode. There is no phase change. There is no, mechanics problems. Okay, and it's just very reliable. Okay, as compared with lithium-ion batteries. For lithium-ion batteries, it's definitely have a second life, shorter. But the flow batteries, second life is not any problem for that. Yeah.
I see. I think this is a very attractive point for flow batteries.
Sure.
So I guess my question is, how do you know that it's 20 years? Do you need to run a flow battery for 20 years?
We have we did that in the laboratory.
Oh, for 20 or 30 years.
Yeah, just a particularly designed, to simulate. Yeah.
I see. That's impressive. Okay.
It's not just 20, 30 years. Yeah.
Okay.
Yeah.
My second question is, you mentioned that only around 6% of this electrode is utilized, if I remember it correctly. So what is the challenge of stopping you using the other 40%? Is that about from the material or from the design?
30% of what?
And I think if I remember correctly, you mentioned that only 60%, around 60% of the electrode is being utilized.
Electrolytes.
Yeah.
Electrolytes. Yeah. For flow battery, you need active materials. Okay. Right now, it's most successful material is vanadium. Okay. So vanadium is is bigger, more expensive than other materials. So therefore, we need to increase the utilization of vanadium, you know, in the batteries. So to do that, so we need to design a system, make sure that it's can be uniform distributed. Okay, so one indicator is the current density. If your current density is very high, meaning that you get a higher, you know, utilization of electrolytes. Okay, so currently is only 60%. So in our technology, the flow battery we developed can be 80%.
I see.
85%. So this very significant reduction in the cost, because the material is a major one of the major component of a cost, total cost.
So which means that if you increase the current density, you increase the utilization of material.
Exactly.
I see. That's
so
very
indicator of current density is the indicator of utilization of electrolytes. Yeah.
I see. Is this like also similar for other like power systems, for example, lithium batteries or other kind of batteries?
No, it's different.
Different. Okay.
Yeah.
I see. Okay. Yeah. These are my questions. Thank you very much for your nice, very nice talk and explanation.
Thank you. I think we still have time to have a couple of more questions. Good. So we still have time for more questions. Yes, go ahead.
Thank you, Professor ZHAO, for your presentation. So I'm not professional in energy storage and also the fossil fuel, but I have some question about the system integration of the fossil fuel. So I remember one of my colleagues during my graduation, he studied how to integrate, how to use the waste heat from the fossil fuel to drive some building systems, such as to supply heat. Or I see in your application, I see there are multiple cooling tower on each energy storage station. Maybe I think if is there a way to utilize this waste heat to maybe can improve the efficiency of the fossil fuel in future? Thank you.
Sorry, I really didn't get your question. You're talking about cooling tower. So cooling tower is a power station, you know, power generation, power plants.
Yeah, I see in your fossil fuel energy storage station, there is a cooling tower on the top of the station.
Oh, you my slides, right?
Yeah.
Oh, this actually is a mixture of energy. We get a fossil fuel power plant. We get a new energy, solar PVs, wind farm mixed together as a new power system.
Also, so maybe the heat.
The cooling tower is part of conventional power plants. Yeah. So I don't know cooling tower. What cooling tower is condensed water.
So the waste heat from the chemical process, can it be used for some?
Cooling tower is used to gather rid of heat of you know, working fluids, steam.
Yeah.
So when you use a burner, right? You get a burner boiler to heat up water, and you get a steam drive turbine for power generation, and then you need to get back water. So then you get a cooling tower to cool down the water, steam.
Oh, so
condensed steam to water back to that's a cycle. So this is a conventional.
Oh, it's not used for the fossil fuel.
The boiler you need a heat. The heat can come from burning natural gas, burn coal, burn anything. Like
I see.
Nuclear.
Sorry, because
that's the cycle. Yeah.
Because I'm not recognize the chemical process.
Yeah. It's good. Yeah.
Thank you.
Thank you. Probably we have the last chance to ask questions to Professor ZHAO today. Yes.
Professor Zhao, thank you very much for your talk. I have a following question regarding the lifespan. So even though the battery can run for a long time, what about the efficiency? Is there an efficiency degradation? Because we noticed there is a slide with the efficiency of different cycles, right? So it's very interesting to see that there is a little increasement between several cycles. So I am very interested in that part. Thank you very much.
So when you're running flow batteries, there will be very likely to have a decay in energy efficiency, also in the what is that? Energy efficiency, and also other performance. That there will be performance index can be decayed. One of the major reasons for that is because the membrane is not perfect. For example, in a flow battery, we get vanadium positive electrolytes and negative electrolytes. We have ions, multiple ions in the tanks. So we wish the proton as a conductor between positive side and negative side. But sometimes you get vanadium ions pass through the membranes. So this is going to decay the efficiency. Yeah. So, and other performance index. So meaning that when you get this problem, then you need a solution. You make sure that this ions pass through, you get a concentrated negative side, then you need to get back to the positive side. So we have a solution. We have a technology to make sure that it's not, coming back again. The efficiency and other performance coming back again. Yeah, it's online can be inside be traded. It's not a problem and any no trouble at all. Yeah.
Okay, so so we can expect a quite consistent efficiency, even though it runs for a long time.
Yes.
Okay, thank you so much.
Yeah.
Yes, yes, there's we have some souvenir, right? Okay, there's some online questions. I got
online questions.
Yeah, I like to read the questions. We got online questions. It's in Chinese. 有机液流现在用什么材料最稳定？
Okay. So
that's the tricks that you can have the funding.
Yeah. So we organic flow batteries, and that is a new technology compared with vanadium flow batteries. So organic, we have different. We needed to create molecules which can discharge and be discharged. Right now, we in my group we developed many different molecules, but it is true that many of them are unstable. We need to improve that. Yeah. So, but I don't remember which one is better. It's a good question. Yeah, I think. Yeah.
Yeah. Thank you. Thank you. We have some souvenirs. Thank you all for attending this the talk and the discussion. Thank you so much.